Well, this is the last class in the semester, last digital class. We'll cover DRAM and so repeat something we're going to cover in the final exam. If you didn't pay attention to it, I will just skim through that really quick. So for example, if I ask you to name 2 fabulous companies in the semiconductor industry, fabulous, or 3, I don't know. Can you? Fabulous means they don't have foundry. It's just digital design, analog design, mixed signal design. When you are searching for jobs, you can see, some of the titles: mixed signal IC engineer, analog, RF, digital, or verification. All different titles. So mixed signal means analog and digital. So what are they? ADCs, DACs. It's mixing analog and digital, right? And analog, it's normally analog and RF together, because if you go to graduate school, when people are getting grants to do any analog circuit design, it's normally RF. Not too many people are just still researching memory circuit design or anything else. There's not too many things to still need people to invent, because already super established. But RF still, because we used to have 4G, depends on the technology. Sometimes we're getting so all those transistor sizes are getting scaled down, getting smaller and smaller sizes. So you can run the circuit way faster to process the digital signal. So we have experienced 4G, 5G, and 6G probably in the future, in the near future. So there's still a lot of things to do for RF. For the analog circuit groups, you'll see probably 90% of the analog groups are doing RF circuit design. And digital is pretty much everywhere. Start with SoCs, system on chip, so including CPUs, memories, and everything, just do digital design. But eventually you can see 80% of the SoC engineers end up with FPGA design. Not too many people can really fabricate their IC chips, and they find out just verify everything on FPGA is just super simple, and they can get products much faster than this. So especially in colleges and universities, you can see a lot of people are doing FPGAs and publish their results on FPGAs, but not SoCs. But still quite a few, but not as many as FPGAs. So fabless means the companies are just doing FPGA verification design, and they will send the design to the foundries for fabrication, but they don't have foundries. Can you name some of them? You still want to do a search, right? I'm writing down the names, but you still want to do a quick search if you have time, just a couple minutes. These are really good companies recently, profitable. IDM, integrated. Can you name a couple of IDM companies? Integrated devices manufacturer. So they have design teams like these: mixed signal, analog, RF, digital verifications. They have all these design engineers, but also they have foundries. Intel, Samsung, TI, okay. And the third category, pure play foundry. Can name 2 or 3 pure play foundries? TSMC, the biggest one now. But do we have another one for IDM? Micron, right? Where's Micron? Where's Micron? Boise, Idaho. Making DRAMs, the biggest company for making DRAMs. It's a nice place to live. It's not, the real estate is not that expensive as California, but the salary is pretty good. That's a good place to live, Idaho. My favorite is 3 states. I don't know, 3 or 4 or 5, I don't know, but Idaho, Colorado, Utah, Arizona, maybe? No, I don't know. People are moving in compared to the east. On the east coast, the people are moving out. But I'm not a desert guy. I don't want to live in Nevada that much. Like Nomadland, right? Did you watch that movie? Not yet. Nomadland, pretty good one. Pure Play, TSMC, Global Foundry, Global. Anyone else? UMC, the second biggest one in Taiwan. There are many others. Many others in the USA as well. Just so many, but not too many of the foundries can do 5 nanometers, 7 nanometers, 10 nanometers. So most of them are doing, still 28, 65, something like that. So if I ask you these questions, make sure you can answer that in the final exam. It's just great booster. It's just giving you that credit. You just need to memorize it real quick. Okay. There are so many others like Broadcom. So it's also a really good company. So if you are looking at the CPU on the Raspberry Pi, if you have played with Raspberry Pi, it's from Broadcom. And when the technologies are commercialized, so I'm going to start from 180 nanometer, and then 90, 65, 22, 10, 5, and 2. What's the size of an atom? 0.03 to 0.3 nanometer. So this is just a few atoms. We couldn't make it smaller than an atom. So when these ones are commercialized, the answer can be a little bit different. Can be plus minus 1 year. Depends on where did you find the answer, right? If you Google it or something. But I mean, plus minus 1 year is fine. You couldn't say this is commercialized in 2021, right? This is a 1999 technology. That's a 2003. That's a 2005. 22 is 2012. This is 2016. 2020. 2023. And eventually, it's not following Moore's law anymore. So what is Moore's law? Yes. So I'm going to ask you this question on the final. Make sure to answer that question. It's just everywhere. You can search it on Google. Is it being doubled every year? every 2 years, right? Every 2 years. Sorry, I didn't tell this correctly last time. So every 2 years, it's going to be doubled. So from here to here, 2 years, not really. Here to here is 4 years, not really. So this statement was made, I think, long time ago, probably 1980s or something. So it was accurate by that time, but now it's not. It's reaching the limit. But you need to know that, okay? When people are talking about it, you know what is that. And also make sure you know how to describe the reading and writing operation for the SRAM. Yeah, I think that's pretty much everything. Also refer to the final exam review lecture. Make sure you go back to that video and watch it in order to prepare for the final exam. Okay. And before we move to DRAM, I'm going to show you one interesting thing I just found, because I remember a couple weeks ago in a lab, I just did a random search with James, and I saw a die of 8266 to the ESP. Did you use it in microcontrollers, right, for the wireless communication? And that's a die shot of the 8260. You can see there are so many things. These coils are inductors, and they also have all the other RF circuits. But what are these ones? I was thinking they are memories, but actually they are not. You don't need that much space for memory. So what are these? No. So these dots are vias. So since you can see these traces super clearly, so they are actually the top metal layer. It's not necessary to be metal strip, because I'm pretty sure they have, this is 40 nanometer technology. So they may have like 5-6 layers of metals, I don't know. But, they have the metal layers on the top like this for what? It's covering pretty much 50% of the space. No. Let's see these ones. You couldn't see clearly, but probably only, these are the top metal, and these traces are probably the metal layer just below it. But I'm pretty sure you couldn't see transistors. They are at the bottom layer, right? So why they are not covering this place? It's a coil. It's an inductor. It's used as a PA, which is a power amplifier for the RF circuits, amplifying the RF signals since they are weak. RF is just everywhere. Wi-Fi and just everywhere. They're super weak. You need to amplify it. So these are used for covering the structure of the circuit, so people are not able to reverse engineer it. So that's why they place the top metal layer here to cover all the main stuff. But they cannot cover these ones because the coils are on the top metal layer as well. If you cover it, it's probably going to affect the inductance. So you couldn't do too much here. But these ones are just pure digital signals. Let's just cover it to protect the IP. And so when people are, engineers, so this is a Chinese company in Shanghai, and I'm pretty sure the engineers, when they are designing these circuits, they have the IP cores. They can directly just buy that CPU core from any IP vendors, like ARM. This is not ARM, but it can be a different company. You can search for it, different company. But they are selling these IP cores. So it's just directly a black box, the CPU with inputs and outputs. So you can directly place it in your design tool, normally Synopsys or Cadence, and then you can, connect. You just use it as a top, and then you connect all the other ones with that black box, and then wrap it up into another top layer. But you don't know what's inside the CPU, because the IP core vendor is not going to tell you what are they. but they will provide you with RTL, register transistor level, right? Language. Did you learn this in embedded devices? RTL, kind of. So ITL is when you're comparing to behavioral, the behavioral code, the language, right? So you can describe a hardware either in behavioral or RTL. So behavioral is sometimes not synthesizable. It's just describing like when this happens, it's like a C language. If this, then do this. When this, do this, right? But RTL is different. RTL is totally synthesizable because you are directly telling the hardware to synthesize what you have written in the environment into a hardware circuit. For example, if you write this in analog, in Verilog, it's going to be synthesized as this. This is super clear. Right? It knows this is on gate. So that's RTL. But however, if it's a behavioral, then sometimes it's probably not implementable. You just couldn't synthesize it into a hardware, cannot implement it in the hardware. You can, since you can describe the behavior whatever you want. It's just totally from your brain, your mind. But not necessarily it's going to be able to be synthesizable, right? So you can buy RTLs. All the CPU cores are being sold in RTLs. You can buy it. But since the RTL for the CPUs, you can imagine the size of the script will be I don't know how many lines, maybe millions of lines. So who can interpret that? It's pretty hard to understand what's going on. Behavioral is very easy to understand because from humans' mind, so you can read the behavioral really easily because you can understand the logic. If this, do this. When this, do this, right? But when you are looking at a very complicated logic, you probably don't know. You can understand, oh, this is AND gate, this is OR gate. But why we need to AND and OR here? It's already being simplified from the very complex behavioral. The engineers has already designed that behavioral and converted into the RTL. So, but when you are reading RTL, it's very difficult to go back. How can you reverse that direction? Such things has been simplified from the KMAP or anything else similar. You cannot go back, right? So it can very difficult to understand RTLs when you are reading it. But when after you fabricate it into chips, you just look at the chip, the die under the microscope. You can see the structures. You can probably duplicate it a lot of times. They will look at the metal layer, just even though they don't know what's going on, they just trying to duplicate all the connections. Since you can see every single connection. So on the top metal, you see the connection, duplicate it, draw that schematic, and then etch it. So there is a very specific acid you can use to etch every single layer, and then you can look at the second layer and then duplicate it, and then the third layer until the very bottom layer. So you can reverse engineer everything, right? So sometimes they were trying to protect their IP or their layout design. They will put some dummy circuits in there, trying to confuse people. It's not totally not useful at all for the circuit, but just trying to confuse people who are trying to reverse engineer the circuit. It happens a lot. But I think this one is just trying to cover as much as they can, right? If they don't do it, I'm pretty sure somebody etch the very top layer, they can still see something, but it's more difficult than if you don't cover anything, right? So they just do whatever they can. Yeah. Yeah. We used it, right? Did we? Oh yeah, it is still, but the upper version is right now is ESP32. So 8260 is just super cheap. It's way cheaper than 32. I think it's less than $3 right now. I can buy one 8266. but ESP32 is a bit more expensive than that. So here's a question. So we learned Flash, right? Flash uses floating gate to be programmed. So what's the voltage to program it? 20 volts, 25 volts sometimes, just high voltage. But for the small technologies like 40 nanometer, if you apply 20 volts, it's going to blow up everything. So but still, when we are programming ESP32, we can still store the program in there, and we can still run it, right? Why is that? So think about that. When people are talking about, hey, IPGAs are fast. IPGAs are way faster than microcontrollers. Like at Mega 322, it's being fabricated in 350 nanometer technology from TSMC. It's huge transistors. That's why it runs slowly. Right? That's why it's a very basic microcontroller. Only $1 can buy one. Sometimes, if you buy 1,000, probably it's less than $1 for the Arduino CPUs. It's a real old technology, 350 nanometer from TSMC. Sometimes there might be different versions, but I think the very common version will be 350 nanometer technology. So, if you make the transistor bigger for the flash, probably it is able to handle the 20 volts. So when you are running the bare-bone microcontroller on the breadboard, you don't need anything else, right? Which means the flash is right in the chip, right? You just grab the chip and plug into the bread. You don't have another flash chip externally, and can directly burn the program into the microcontroller, and it runs. It memorizes all the programs, right? When you power it off, it's not losing any information. You can still run it next time you power it up. So the flash is directly inside the chip. But for the 40 nanometer technology, the ESP32, I don't believe it's able to handle that 20 volts stuff, voltage power supply easily. So that's why, and also, as a high performance microcontroller, it needs a lot more memory or flash to store their programs so they can run a large scale design. So that's why the flash of ESPs is off the chip. It's another IC just beside it. So you can see on the ESP chip you have used, it has a little cover, the metal cover. If you remove the cover, you can see there are multiple chips. It's not one microcontroller. So the microcontroller is the microcontroller, you can see it. But also there are several other chips. Except for the resistor capacitors, there's another big IC, which is the flash, and it's the SPI flash. So which means it's communicating with the CPU through SPI, use the flash through SPI. So whenever you power it up, it is able to read the program from the flash through SPI to where? So you are not storing the program inside the CPU, right? Because the flash requires higher voltage to attract the electrons into the floating gate. But however, so that's a design strategy. So because we want the CPU to run faster, so that's why we need a smaller technology. And it's going to be 20, 40 nanometers. We want the CPU run faster. And so that's why we cannot keep the flash on chip. So it has to be off the chip. And so we need to read the program from the flash every time we run it, so it knows what to do. And the program will be read into DRAM in the chip. DRAM does not require, I'm going to do this really quick, doesn't require high voltage. And it's volatile, which doesn't matter because flash is non-volatile. So the flash of the chip can memorize everything. But DRAM will just temporarily receive everything through SPI from the flash and send it to the CPU to do the calculation. Okay, and it's DRAM. And also the CPU, when CPU is doing the calculations, the SRAM very close by to the CPU is being used to store the instructions and registers temporarily, because SRAM can run really quickly. It's used as cache just beside the CPU. But DRAM is being used as regular memories, but volatile. So DRAM can get the data from flash, and then when the CPU is doing calculations, it's going to communicate with SRAM in that case. Not all the same, but this is just general structure about how things are being done. So let's look at what are DRAMs, okay, really quick. Also, you need to know in the final exam you want to know the answer to the acronyms. So what is SRAM? What is DRAM? What is SDRAM? So DRAM is dynamic random access memory. It uses a little capacitor for each memory cell. So if I draw the schematic, it looks like this. And first, you need to know why it's called DRAM. What's the difference? Why it's called dynamic, not static? So that's the bit line, that's bit 0, bit 1, bit 2, and all these little capacitors are the capacitor of the memory bit. They're all the same, they're all the memory cells. Dynamic, because the CM bit caps are leaking charges through the anodes. Yeah, definitely, if you give a 0, all the anodes are off, but they won't be perfectly off. So the charges are leaking through the anodes gradually. That's why it's called dynamic dynamic RAM. So after a while, you have to reset it to recover all the memory bits in there after a certain period of time. So that's why it's volatile, because it's leaking. But why? Also, SRAM is also volatile, right? If you part it off, then you're going to lose everything. But however, it's static. So why is SRAM is static? Why is this not static? So this is not static because it's leaking. So why is SRAM is static? Yeah, use the latches. It's a positive feedback, right? So here's the SRAM. And it is able to, so here is a Q bit, that's a data storage bit. It is able to hold that charge or the bit value stably because it's a positive feedback. It's going to pull the bit here to VDD or ground either way. It's a positive feedback. It's going to do this or this. As long as you have the power supply, it's going to be very stable. Even though it leaks sometimes, but it's fine because whenever it leaks a little bit, it's going to be recharged by the power supply again. to pull it up to VDD. That's why it's static. The DRAM doesn't have that power supply to do it. So it's going to leak. So flash, so these two are volatile, right? So flash is not volatile because flash has the charges being trapped in where? Huh? Poly 1, the floating gate. So, but you are still thinking that I got some charges stored in the floating gate that's non-volatile, but is it non-volatile forever or just for a few years?
Probably a few years.
Just a few years. So you probably don't know that. You don't want to store your data into the USB drive forever. If you have really precious photos and you want to put it into the USB drive. But if you plug it in back to your laptop pretty often, that's fine because it's being recharged. However, if not, you store the data into the USB drive and put it into the drawer and won't use it for 10 years, you're going to lose the data. So the average lifespan for the data can stay in the USB drive is 10 years. That's why it is non-volatile, but not forever, right? Just keep in mind. The hard drive, yeah. So here is a memory array for the DRAM. So we need to know how can we read and write into these memory cells. So first, since we want more memory for the chip, so whenever you are selling your microcontroller, you're telling people I have 32 kilobytes of DRAM compared to only 2 kilobytes DRAM. It sounds like better, right? Because you have larger memory, so you can run more programs. So in that case, we want to integrate more memory cells, and you have laid out one capacitor in one of the homework assignments. You know caps are taking space, so you don't want to make the cap too large. The trade-off is if you keep the caps tiny, for example, 20 femto, for example, so the metal traces running in the memory cell even has a larger capacitance compared to the memory. So you probably are asking, so all the parasitics can be 200 femto. Femto is a very small unit, right? But you are probably asking, really, who is a memory? Is this a memory or is this a memory? This is even larger, right? So you do need, that's fine because as long as you can have a circuit which can sense 0, 1 in here, you're done. You don't, even though it's smaller than this, which is fine, but you just need a sensing circuit. So there are two types of sensing circuit. One is called NSA, one is called PSA. So the NSA is used, it's an NMOS sense amplifier. This is PMOS. So if you want to pull it up all the way to VDD, you need this one. If you want to pull it down to the ground, you need this one. So you need both because it can store 0 or 1. You don't know. And what's the theory running behind it? So whenever the word line is being switched on, you can imagine it's going to be one cap, one smaller cap on one side, which has either 1 volt or 0 volt stored in there previously. And there will be another bigger cap on the other side, and there will be a switch to control that on and off. So whenever this is on, it's going to short these two caps together. So this is called the capacitance of the column. That's a column line. It's a parasitic. It's not a real cap. So what's actually happening is you can model that behavior into this circuit. So here is a column capacitance. For example, it's 200 femto because the metal lines are even having a larger capacitance compared to the memory bit, which is 20 femto. So whenever this is closed, what's going to happen? Keep in mind, we need to pre-charge. We need to pre-charge the bit lines, which is here, to half VDD. If the VDD is 1 volt, it's going to be 0.5 volts. That's how I operate the DRAM. So I'm going to show you why really quick. So keep in mind, whenever you're resetting everything, you need to pre-charge it to half VDD. Just memorize it for now, okay? And for this one, you don't know because this memory bit can store 1 volt, can store 0 volt. Doesn't matter. So now let's look at the 0 volt case. What's going to happen here? Whenever this is being switched on, then the charges will be averaged into these two caps because it's going to share this line, so it becomes a one cap, right? So V final equals to Q final over C final after you switch it on, after you close the switch. And what is the Q final? Q final equals to the Q here and Q here. They're just being added together. You're not losing any charges. They're just sharing. So for this one, it's a 0 volt times 20 femto plus here's 0.5 volt times 200 femto. So what's the C final? It's going to be 20 femto plus 200 femto. And eventually, you're getting, so this is 0, and this is 100 femto over 220 femto, and this is 0.45 volts. So in that case, it's been said, if this memory bit has 0 volts stored in the cap in the memory previously, if you switched on, you are getting 0.45 volts for the bit line. So let's look at the 1 volt case. If this guy stored 1 volt at the very beginning and still pre-charge this guy to 0.5 volts, just pre-charge the bit line to 0.5 volts. And then what's going to happen? One volt this time compared to the 0 volt last time. This will be 120 femto over 220 femto, and it is 0.55 volts. So, if you have 0 volts stored in a memory bit at the very beginning, if you close the switch, you are getting 0.45 volts. If you have 1 volt stored in a memory bit at the very beginning, if you close the switch, you are getting 0.55 volts. So it's like the bit line has an offside, which is 0.5 volts. And if it has a data, which is 1, eventually it becomes 0.55. If the data is 0, it becomes 0.45. So you have a difference. So keep in mind, in binary, you just need a difference. You just need a 2 states. And you're done. You have 2 states. You just need to tell. You just want to, whenever you got this one, you want to pull it right way up to VDD. Whenever you have this, you want to pull it down, way down to the ground. So you're done. It's not 0. Definitely it's not 0. But since you can tell the difference, I'm going to define this one as 0, this one as 1. So now you need a sensing circuit. You just need a sensor, right? You just need a sensor. Whenever you have 0.45, you sense it. I give a 0 to it. So what the sensing circuit looks like. down here, do this. It's another example of positive feedback. So think about it. So you have parasitics here, the C column. It's just everywhere. Parasitics. So now let's see. If I got 0.45, remember? Whenever the memory stores 0 volts, I'm getting 0.45 for the bit line. So if I'm getting 0.45 after I close the switch, after I activate that line, and what has been stored here is still 0.5 volts as pre-charged, 0.5 volts. What's going to happen? As a positive feedback, keep in mind. And whenever this is on. So these two transistors, this is 0.5. It's going to turn on this guy, right? This is 0.45 volts is also turning this guy on as well. However, the source of these two transistors are being shorted because this is on. You are sensing, just give a rising edge. So both of the two sources are being shorted to the ground. So what's happening is they are both on, but they're competing with each other. So which is being turned on more at the moment whenever you are firing the memory cell? Which one is being turned on more? The left one is being turned on more. So what means is it's going to start pulling this point to the ground earlier and quicker. So what's going to happen is the voltage here will drop because this is shorted to the gate of the right one. So the right one will be shut off. It's a positive feedback because whenever this is on, this is a bit larger than this at the very beginning, then this will be on more. So it's going to draw more current. So it's going to draw this, will pull this node down to the ground quicker. So it's decreasing quicker. It's shutting off this one quicker as well. So eventually, this will stay at 0.5 because it's totally being shut off. But this will be totally pulled down to the ground. So what's the voltage here will be left? This will be fully on. This will be fully off. Maybe it's probably just lost some charges, can be a little bit lower than 0.5. But doesn't matter because it's already shut this off, so it's not conducting any current anymore to the ground. But doesn't matter since we're going to pre-charge it to 0.5 volts in the next cycle. So we're not reading it. But however, for this guy, because it's a positive feedback, this node has been pulled down to the ground. So what's the voltage left here? 0 volts. Very close to 0 volts. So initially you have 0.5 volt, 0.45, no, you have 0 volts stored here. After you close the switch, because of the parasitic capacitance of the traces, when you close the switch, this 0 volts cannot be delivered to here to read. It's being averaged out, and you cannot change it because the physical capacitance of the traces, you cannot change it. So whenever you close the switch, you are going to have a 0.45 volts instead of 0. But however, since you have this NSA, the NMOS sense amplifier, it's a positive feedback, it's going to pull this down to the ground eventually. So you are reading zeros. So now let's look at the same circuit if I have a 0.55 here instead of 0.45. Remember, if you have 1 stored in here at the very beginning, you're going to have a 0.55 volts eventually left. So if you have 0.55 volts, can you pull it right up to 1 volt? Since you want to read 1 volt. Can you or cannot? You cannot, because there's no VDD to pull it up. You don't have that path. So this guy can only read a 0 but cannot read 1. And also, there's another problem for this guy. For example, this is array 0. And this is the ideal case. But however, the column capacitance over here can be different compared to here, because this is being used as a reference. The capacitance will be very different from this one. So when this is being discharged, it's a mismatch compared to the two sides. So the way to solve this problem is to have another, let's just connect the drain here, all the drains here, to another array. Right? So you can balance the capacitance, the parasitic capacitance from these two sides. So they are symmetric. But still, how can we pull it up to the, so these are the bit lines, right? That's bit 0. So you can extend this line to the top. So you need something on the top. That's PSAs. So PSAs looks like this. So these are the bit lines. That's a parasitic column capacitance. See if this makes sense or not. Just connect these two to here on the top. So how this works? Take a look at it quick. So here's a bit line. If I got 0. Since the PMOSes are being used to sense ones, so I'm assuming this is 0.55 volts. So this has been pre-charged to 0.5 volts. So what's going to happen? Which one is being turned on more? The lower one. So this is being turned on more. If this is being turned on more, this will be directly pulled up to the VDD. So whenever it has 0.55 volts, it's actually 1 volt eventually because of the positive feedback. So you just need the two. You need both. PMOS, the PSA, and the NSA, both for the memory cells. So for here, for this column, you need this NSA here, and also you just add a PSA on the top, which is this one. So you are thinking, how do I sense it in that case? I have a sense P, I can turn on this sensing amplifier. Also, I have a sense, I have a switch here for the NMOS as well. Does that matter? Since we don't know if I have 1 or 0 stored in the memory bit at the very beginning, how do you know which one you want to sense? You have 2 switches, one for N, one for P. Does it matter? You just fire one and then fire another one, then read, right? Because if, for example, you have 0.55 volts here at the bit line, then you fire this one, it's going to be put up to VDD. And then you fire NMOS, it's not affecting anything. And then if you have 0.45 volts here, you fire this one, it's not doing anything. Then you fire this one, it's going to be put down to the ground. You're still reading zeros. You have to do both. And we do have a simulation circuit to do this. Let's take a look at it really quick. So I'm going to directly show you, since given the time constraints, I'm going to directly show you the final version. So that's a DRAM cell with a PSA and NSA. So I can assign a initial voltage for the memory cell, which is here. That's a memory cell, right? So look at the initial value for the memory cell. One. So I got a 1 stored in the memory cell. Then let's see if I can read a 1 from the bit line here. I'm going to run. So eventually it's being put up to 1. So what are these ones? I have an equalizer which is giving the precharge. You can see this voltage is half VDD, 0.5 volts. So I have the 2 channels of the NMOSes. Whenever I turn this on, it's doing what? Look at these 2 lines. Bit line 0, bit line 1. I initially assign an arbitrary voltage to them. One is 750 millivolts, one is 250 millivolts. Right? Whenever I fire this equalizer, which is feeding a 0.5 volts to here, the 3 transistors is called a voltage equalization circuit. So whenever I turn on the channel, this 0.5 volts will be delivered to here and here. Okay, you have a bigger one. If you remove it, it's not changing anything, but it's just trying to make the channel wider so you can further equalize the 2 lines to make it 0.5 volts. So you can see, boom, I turn on the equalizer, I'm getting 0.5 volts for the 2 bit lines, right? And then it's going to keep that value until when? Until here, something happens. So what is that? So I start sensing something. Doesn't matter for the N-sense because it's not doing anything. We care about the P-sense. So after we turn on the PMOS sensing circuit, you can see the bit line will be pulled all the way to VDD. And the other one is being pulled all the way down to the ground. Why? Because the NSA. The PSA is pulling everything to VDD, the NSA is pulling everything to ground. Okay, that's how you sense, how you fire the memory cell and sense the data from the DRAM. Okay, so Dr. Baker is a DRAM guy, and he has a textbook written 20 years ago. It's called DRAM Circuit Design, which is probably one of 2 or 3 textbooks available on the market for memory cell designs. If you are interested in that, you can read it in the future. And the IC design is a really rewarding industry. go to graduate school. I highly recommend it, and try to fabricate one or two ICs, and you can easily get a job. And very hard, so not too many people can replace you in the future, because you can see the bar is high. Not too many people can experience this kind of like education and labs. Doesn't like software. You can sit at home and just program from an online course or something, and you can get a job easily. But for the IC industry, the bar is high, and it's also very rewarding. All right. Thank you for the wonderful semester.